This dwelling has received official sanction from the United States government, attesting to its capacity to endure catastrophic weather events such as EF5 tornadoes and Category 5 hurricanes. It achieves substantial reductions in energy expenditures by as much as 75%, and insurance premiums by up to 90%, while possessing the structural integrity to last for many centuries, entirely free from concerns of decay or infestation. Nevertheless, in the current landscape of America, a nation where over 1 million new residences are erected annually, fewer than 900 of these innovative homes are in existence. This architectural marvel is known as a monolithic dome, and this is the narrative of the family that revitalized its design. We will delve into the intrinsic qualities that render it virtually impervious to destruction and the systemic obstacles that the government imposes, making its construction exceedingly arduous for the average individual. The concept of the dome is far from a recent innovation. In fact, it represents the most ancient structural paradigm humanity has ever conceived for the creation of enclosed spaces. Approximately 19,000 years ago, in the region now recognized as Ukraine, primitive builders fashioned habitations by utilizing mammoth tusks and animal hides, ingeniously bending them into curvilinear forms. These early artisans lacked sophisticated mathematical knowledge, established engineering principles, or written guidance. However, they possessed a profound understanding derived from keen observation. The curved configuration effectively deflected wind, distributed loads uniformly, and remained steadfast when conventional flat structures succumbed to the elements. Even 17,000 years prior to the invention of the first concrete mixture, the dome already offered a solution. By the 2nd century, Roman architects had grasped a principle that would take the Western world an additional 18 centuries to fully comprehend and embrace. The rotation of an arch a full 360 degrees around its central axis generates a three-dimensional shell capable of distributing loads in every direction simultaneously. In the year 125 AD, they applied this profound understanding to construct the Pantheon in Rome, a testament to the largest unreinforced concrete dome ever erected. Remarkably, after enduring nearly 2 millennia of seismic activity, inundation, and military conflicts, this edifice continues to stand today. The inherent strength and versatility of the dome are evident across historical epochs and diverse civilizations. The igloos constructed by the Inuit people exemplify a catenary dome formed from compacted snow, meticulously shaped to channel the structure's weight into compressive forces rather than susceptible bending stresses. A hemispherical form, when subjected to stress, tends to fracture, whereas a U-shaped catenary profile inherently resists such failure. Wallace Neff demonstrated a profound appreciation for this principle when he pioneered and erected the inaugural Bubble House in 1941. This pioneering effort ignited a new wave of dome construction enthusiasts, including the South Brothers, who, in 1976, articulated a clear understanding of the engineering tenet that a continuous rounded shell offers superior structural performance compared to any other form of enclosure. However, they also came to recognize the inherent difficulties associated with such a design. Following extensive experimentation with geodesic configurations, inspired by the work of Buckminster Fuller, David South repeatedly encountered the same fundamental challenge. The proliferation of thousands of connection points translated into an equivalent number of potential points of ingress for water and significant material wastage. The truly revolutionary advancement emerged in 1975, echoing the pneumatic innovations of Dr. Dante Bini's earlier Binishells, when they developed a novel process that inverted the conventional methodology. This new approach yielded a more robustly insulated and permanently constructed structure. The outcome was a single, seamless, steel-reinforced concrete shell measuring 105 feet in diameter and 35 feet in height. This initial experimental project proved to be a resounding success, leading to the patenting of their innovative process in 1977 and 1979. Merely 2 years later, they utilized this very construction method to erect their own family residence. This dwelling, christened Cliff Dome, quickly became a significant point of interest, with guided tours of the property being conducted up to 4 times each week for visitors from around the globe. The palatial 8,000-square-foot residence boasts 8 bedrooms, 4 bathrooms, a full-sized volleyball court, and an indoor garden, and was regarded at the time as the zenith of monolithic dome engineering. But how precisely did the South brothers achieve the construction of their monolithic dome residences? And perhaps more crucially, what attributes bestow upon them a demonstrably superior durability and thermal efficiency compared to conventional housing designs? The process commences with a circular concrete ring beam embedded into the foundation. To this beam, the construction crew securely fastens the airform, a custom fabricated membrane crafted from PVC-coated polyester fabric. Powerful air blowers then inflate this membrane, creating a pressurized fabric enclosure. Individuals enter this space through an airlock, and once inside, the actual construction phase begins. The initial material applied to the interior surface is a layer of closed-cell polyurethane foam, sprayed to a thickness of approximately 3 inches. This foam serves a tripartite function. It establishes a thermal barrier boasting an R value exceeding R20, provides the necessary structural rigidity to support the steel reinforcement and concrete prior to curing, and acts as a framework for the subsequent attachment of rebar hangers. These hangers are installed next, comprising horizontal hoops and vertical reinforcing bars meticulously interconnected across the entire curved surface in 2 distinct orientations. Following this, the application of shotcrete commences, a specialized concrete mixture propelled at high velocity through a spray nozzle. Its high-speed application ensures a denser compaction compared to conventional poured concrete. The shotcrete is applied in successive layers until the shell attains a thickness ranging from 3 to 12 inches. Upon curing, the result is a singular monolithic piece of steel-reinforced concrete, extending from the foundation to the very apex of the structure. Engineers estimate that such a design possesses a lifespan measured in centuries. A critical element within this construction methodologies significantly enhances thermal retention. In conventional homes, insulation is typically situated within the wall cavities, separating the interior living space from the external environment. Conversely, in a monolithic dome, the insulation is positioned on the exterior. Consequently, the substantial mass of concrete, weighing hundreds of tons, resides on the interior side of the thermal barrier. Once the interior space is heated or cooled, the concrete mass absorbs and retains this thermal energy, gradually radiating it back into the living area over an extended period. However, the exceptional energy performance is merely one advantage offered by the dome structure. Its remarkable resilience in the face of extreme weather conditions is truly its defining characteristic. The inherent catenary curve of the dome efficiently redirects all applied forces, including the weight of the structure itself, snow loads, wind pressure, and seismic stresses, directly into the foundation as compressive forces. This design eliminates vulnerable corners where wind can exert leverage to dislodge a roof and avoids flat wall sections prone to pressure buildup that could lead to structural failure. A wind speed of 300 miles per hour exerts approximately 404 pounds per square foot of pressure against a flat vertical surface. In stark contrast, the same wind flows smoothly over and around the curved exterior of a dome, as there is no flat surface for it to impinge upon. Federal safety standards for tornado and hurricane shelters classify monolithic domes as providing a level of protection that is virtually absolute against EF5 tornadoes and Category 5 hurricanes. To achieve such a designation, a structure must successfully withstand the impact of a 2 by 4 inch lumber piece traveling at 100 miles per hour. Against a standard brick veneer wall, this projectile would easily penetrate. However, against a 3-inch thick dome shell, it would cause only a superficial abrasion. The structure's resistance to fire is equally impressive. The steel-reinforced concrete shell of a monolithic dome classifies it as a Type 1 or Type 2 fire-rated structure according to the International Building Code, rendering it effectively fireproof. Numerous real-world instances have validated the efficacy of these buildings. From an economic standpoint, a school district in Wisconsin constructed 5 monolithic dome facilities for a total cost of $9 million. The dome design resulted in an estimated saving of $8 million for the district compared to conventional construction methods, even before the commencement of utility expenditures. Their superior energy efficiency has also been demonstrably proven in diverse settings. In Mesa, Arizona, a locale experiencing temperatures exceeding 100 degrees Fahrenheit for 7 days annually, a 3,000 square foot dome home recorded a maximum monthly electricity bill of $199 during the peak summer cooling season. This contrasts sharply with the average peak summer electricity bills for similarly sized conventional homes in the Phoenix metropolitan area, which range from $400 to $600, according to data from Arizona Public Service. Meanwhile, in Virginia, one family documented annual energy expenses of $900 for their 2,600 square foot dome residence a sum less than what most Americans allocate for heating a single-bedroom apartment. However, the discussion of energy efficiency almost recedes into the background when one examines the remarkable record of disaster resilience. In May of 2003, a tornado traversed directly over a 40-foot dome home situated in Polk County, Missouri. A conventional home, nearing completion a quarter-mile away, was violently torn apart and deposited into a nearby forest, while the damage sustained by the dome was limited to a single piece of window trim. Following the devastation wrought by Hurricane Katrina in 2005, the New Life Family Church in Biloxi, Mississippi, stood as one of the few substantial structures remaining intact within the city. Concurrently, a dome home in Pensacola, Florida, successfully weathered a consecutive onslaught of 3 hurricanes, Dennis, Ivan, and Katrina. Perhaps the most extreme test on record occurred in 2003. A government building constructed with monolithic dome technology in Iraq sustained a direct impact from a 5,000-pound bomb. Although the interior was obliterated, the dome structure itself remained remarkably intact. Presently, there are close to 4,000 of these structures distributed across 49 states and 53 nations, serving a variety of purposes including residential dwellings, places of worship, and community centers. Given the underlying physics, the FEMA certification, and the extraordinary track record in disaster situations, it prompts the question, why are there only approximately 900 such homes in a nation that constructs over 1 million new houses each year? The probable reason we do not all reside in these structures can be attributed to bureaucratic complexities. In the United States, the acquisition of a mortgage is contingent upon a property appraisal. A standard mortgage appraisal mandates that the appraiser identify 3 comparable properties in the vicinity that have been sold within the preceding 12 months. This appraisal system was conceived for a housing market that is overwhelmingly composed of rectangular wooden structures. Monolithic domes, however, are a rarity, their proprietors having invested in a dwelling that incurs lower operational costs and is likely to endure for generations, seldom put these properties on the market. Consequently, for the majority of appraisers and in most real estate markets, locating 3 comparable dome sales from the recent past is virtually impossible. In the absence of comparable sales, lenders perceive no discernible market value. Without a determined value, a mortgage cannot be secured. And without a mortgage, the pool of prospective buyers contracts significantly, largely restricted to individuals capable of paying cash or arranging financing through a local credit union. A diminished buyer pool inevitably leads to fewer domes being constructed, which in turn perpetuates the scarcity of comparable sales, thereby hindering mortgage approvals. Furthermore, zoning regulations introduce an additional layer of impediment. Numerous municipal ordinances stipulate a minimum roof pitch to maintain aesthetic uniformity within neighborhoods. The surface of a dome transitions from a vertical orientation at its base to a horizontal plane at its apex, meaning it technically fails any fixed pitch requirement at every point along its curve. In certain states, such as California, obtaining a building permit for a thin shell concrete structure, which local inspectors may have no prior experience with, can incur engineering review fees exceeding $40,000 even before any concrete is poured. No deliberate decision was made to prohibit the construction of these rounded homes. Rather, the existing systems were simply not designed to accommodate them, instead prioritizing mass-produced, profit-driven alternatives. However, for those individuals contemplating the implementation of a monolithic dome design for their upcoming construction endeavors, there are several crucial considerations to be aware of. Primarily regarding cost, as securing a conventional mortgage for construction may prove more challenging, it might be necessary to personally finance the initial outlay. The concrete shell itself, prior to any interior finishing, typically ranges from $75 to $100 per square foot, a cost generally comparable to a mid-range conventional construction project. It is essential to remember, however, that the most substantial financial benefits are realized over the long term, with energy bills reduced by 50 to 75%, significantly lower maintenance requirements due to the absence of decaying wood, the need to replace roofing shingles, or the potential failure of frame joints. For financing purposes, the most effective strategy that has proven successful for dome builders involves approaching a local community bank or credit union rather than a national lending institution. It is advisable to frame the project as a construction loan rather than a standard residential mortgage. Collaboration with a licensed general contractor who can present a comprehensive project proposal is also highly recommended. Furthermore, if an all-masonry insurance rate can be secured, premiums may be between 50 and 90% lower than those for a standard policy. However, the most effective method for acquiring comprehensive knowledge and becoming thoroughly informed about these structures is through the Monolithic Dome Institute. They routinely host intensive 5-day hands-on workshops in Italy, Texas, with tuition fees ranging between $2,000 and $2,500. During these 5-day sessions, participants actively engage in the construction process on an actual dome, applying foam insulation, tying rebar, and working with shotcrete. Upon completion, attendees receive construction manuals, cost estimation spreadsheets, and blueprints for small starter domes. These workshops also attract contractors, providing a direct conduit to professionals who can manage the construction if self-building is not your preferred route. The monolithic dome is essentially a steel-reinforced concrete shell, built upon a 50-year-old patent and governed by the same fundamental physics that have sustained the Pantheon for 2,000 years. Yet the financial system has deemed it too unconventional to finance simply because of its round form. A significant portion of the content presented on this channel explores subjects that fall outside the conventional mainstream. This is not because these alternatives are ineffective, but rather due to the pervasive influence of corporations and regulatory bodies that have established more profitable pathways. If these types of issues resonate with you, subscribing and sharing the content is the most straightforward means of ensuring its continued visibility. And if you are interested in discovering a remarkably simple $15 modification that can significantly enhance the performance of your windows, even surpassing that of triple glazed units, I encourage you to view this video.